Let's talk about half-life. For any reaction, chemical or nuclear, that is first order, there is a characteristic half-life, and it is a constant. If we can determine at any point the concentration or nuclear activity of the reactant, and if we know the half-life, then one half-life later, whatever that time is, we'll have 50% of that activity or concentration. Two half-lives later, there will be 25% of the original activity. Three half-lives later, there will be 12.5% of that activity or concentration, and so forth. We can see, for instance, here we started off with an activity of 1,000. After this first half-life, there's an activity of 500. After the second half-life, there is an activity of 250. And so the half-life here looks to be just short of 150 seconds, maybe in the vicinity of 130 seconds. In a second-order reaction, the rate depends on the square of the reactant concentration. Either a single reaction raised to the power of 2, in which case the rate is dependent on some constant times the square of the concentration of that reactant, or two reactants each raised to the power of 1. So in this case we have a second order reaction, but it's first order in A and first order in B. Now the derivation of this particular equation does require calculus, but the reciprocal of the concentration of A at time t is equal to the reaction rate constant times t plus 1 over the original concentration of A. This is true for second order reactions. The equation is also of a linear type. F of t is equal to m times t plus b. You'll remember y equals mx plus b. Now the reciprocal of the concentration at time t is the function of t. K is the slope of the graph, and the reciprocal of the initial concentration of A is the y-intercept. We can recognize a second order reaction then by plotting the reciprocal of the concentration of the reactant against time. If it is a linear function, the reaction is a second order reaction. Moreover, from this equation we can show the relationship between the half-life and the concentration in a second order reaction. Remember, in a first order reaction there was no relationship. The half-life was fixed. In this case, the time at time 0.5, t is equal to 1 over k times the original concentration of A. The half-life of a second order reaction then does depend on the initial concentration. How does this differ from first order? Well, there is no dependence. The half-life is 0.693 divided by the rate law constant. But for second order reactions, it's 1 over the rate law constant times the initial concentration of the reactant. There is a reciprocal dependence of the half-life on the initial concentration of the reactant. For example, suppose K is 0.2 reciprocal second reciprocal moles. If A0 is 1 molar, then the half-life is 1 divided by 0.2 or 5 seconds. But if A is 0.5 molar, the half-life is 1 over 0.1 molar or 10 seconds. You can see this dependence. As the molarity of the initial concentration goes down, the half-life is in fact doubled. The reaction then slows down as the concentration is reduced. That makes a certain amount of sense. Example. In the gas phase decomposition of nitrogen dioxide at 573 K, we see the nitrogen dioxide is breaking up into nitrogen monoxide and oxygen gas. So we get this data on the concentration of NO2. You can track that by the intensity of the brown nitrogen dioxide color. We analyze the data now in two ways. If we take the natural log of the nitrogen dioxide concentration, or the reciprocal of the nitrogen dioxide concentration. As you can see, the graph of the natural log, which for first order reaction is a straight line, is not a straight line. It's a curve. But the graph of the reciprocal of the nitrogen dioxide concentration against time is in fact a directly proportional relationship. It's a straight line. By taking the slope of the line, we see that the rate law constant is 0.543 reciprocal molar reciprocal seconds. What is the half-life from time t equals 0 for the decomposition of NO2 as represented by the table and graph that we just looked at? From the table, we see that the nitrogen dioxide concentration hits the halfway point, 0.005, between 100 and 200 seconds. That's a good thing to eyeball, so that if your calculation of the half-life gets out of that range, then you know you've made a mistake. Using that second order equation, the half-life is equal to 1 over K times the initial concentration of the reactant NO2. We get 0.543, 1 over 0.543 times 0.0100, or 185 seconds.